So we are going to address this overarching question: how do we actually construct an index? So the process of constructing an index is called indexing in IR terminology, and the machine which performs indexing is called the indexer. Now, we already discussed how to construct an index in chapter 1. But if you recall, the simplistic assumption we made in chapter 1 was that our corpus size is small enough that the dictionary as well as the postings lists can entirely fit into main memory. So we could do the sort operation assuming that all our data is in RAM or main memory. Now we are going to drop that assumption and we are going to be more realistic. We are going to move to larger corpus sizes, and for those corpus sizes, it will turn out that the data that we are dealing with, the data that we need to sort, is not going to fit into main memory. So we'll need to discuss how to build the index when your data does not fit into RAM. Could you please switch off the microphone from that end?
Yes, sir.
Yeah, thank you. So before we look at how index construction takes place under 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 a limited amount of main memory, we need to understand a little bit of hardware basics. I assume that you've done a course in basic computer architecture or operating systems. So we'll use some concepts from there, but they won't be very hard concepts. So I'm just going to briefly review uh, the material that we'll be using for this chapter. Now, why are we interested in looking at some of these hardware basics? Well, it's because the design of the indexing algorithms that we're going to talk about in this chapter is entirely governed by the hardware features or constraints that we are going to discuss. So many design decisions in information retrieval are based on the characteristics of hardware. If your hardware was very different, then the techniques and the algorithms would also have been significantly different. So that's the reason why we need to look at some hardware basics. So the first principle that we need to keep in mind here is that accessing data in RAM, accessing data in main memory is much faster than accessing data on disk. If you've done a course in operating systems or computer architecture, you must have studied about the memory hierarchy. How many people have not studied memory hierarchy before? Maybe somebody can take a poll there to find out. I just want to get an idea of whether students have done a course on operating systems or computer architecture.
Yes, sir. We've done a code.
You've done a course? Okay. So you don't need to know too many details there, but I'm just assuming that you encountered the memory hierarchy there. So basically the memory of your computer system can be visualized as a hierarchy. Okay. At the topmost level in the hierarchy are certain kinds of memory. Could you please switch off the microphone? Thank you. So at the topmost level of the memory hierarchy are certain forms of memory that are very fast. Okay, and the fastest one that you can think of is the register, which is located right on the die which has the processor. Then at the next level in the memory hierarchy, you have caches. Okay, so you can have caches of different levels. You can have L1 cache, L2 cache, L3 cache, and so on. And then somewhere after that comes main memory or RAM. And then at the bottommost level, we generally tend to think of disk storage, okay, hard disk. Now the thing about this hierarchy is that as we go up this hierarchy, as we look at higher levels, the higher levels in the hierarchy are smaller. Okay, this means that the size of the registers is smaller than the size of the L1 cache. The size of the L1 cache is smaller than the size of the L2 cache, and so on. And likewise, size of the RAM is smaller than the size of the hard disk. But not only are the higher levels in the memory hierarchy smaller, they're also faster. Now one may ask, why is it that if accessing the register is very fast, accessing the cache is also relatively fast, why don't we make these memory units larger? And that's because the upper levels of the memory hierarchy are also more expensive, which is why they tend to be smaller. And the fourth feature of these levels of memory hierarchy as you go up is that the upper levels are subsets, or the data contained in upper levels is a subset of the data contained in lower levels. For example, what you have in the register is the data that you are currently working with, or or the data that you just were working with. So that data is going to be a subset of the data that's in the cache. And the data in the cache in turn is going to be data that you are presently working with or recently were working with. And that is going to be a subset of the data at the next level in the memory hierarchy, and so on. So as we go down the memory hierarchy, we are going farther and farther in terms of physical distance from the processor. So that particular memory is going to get slower, it's going to get cheaper also, and it's going to get larger. So the space in the hard disk, for example, is much more than the space that is available in the RAM. So this hierarchy is what you need to keep in mind when thinking about um, these hardware constraints that we're going to just talk about. So accessing data in the RAM is much faster than accessing data in the hard disk. The other thing that you need to know about hardware over here is that the amount of time it takes to transfer data from the disk into main memory is primarily governed by what is called the seek time, or the disk seek time. There are actually three delays. There are three separate times that add up to form the total amount of time that it takes to transfer a given amount of data from the disk into main memory. There's the seek time, which is the time it takes for the disk head, to move to the right track on the hard disk where the data is stored. Okay, so that's the seek time. And then once the disk head is on the right track, there will be a further rotational delay before the starting point of the data on the track rotates and finally reaches a spot that is directly under the head. So there will be some rotational delay there. And then it takes some time for the disk head to read the data that is moving under it and transferring it to main memory. Now we are going to collapse these two generically into seek time in this chapter, but remember that seek time is really the time it takes to do a disk seek plus an additional rotational delay. And sometimes the rotational delay could even be larger than the actual time it takes to seek. And note that these times are governed by mechanical constraints, right? Because for the head to mechanically move to the right track and for the track to mechanically rotate so that the data reaches a spot directly under the head, it's going to take a significant amount of time because you have mechanical motion here instead of electronic transfer. So which is why these two times tend to dominate uh, the time in disk transfer. So once the data starts being transferred, it's relatively fast, but it's still slower than directly reading that data from main memory. Right? So if the processor wants to work with data in main memory, it can do so in a much shorter amount of time because of these three delays. Now these two delays are orders of magnitude larger than the amount of time it takes to fetch a byte from main memory into the cache, for example. But even if you look at the transfer time, which is the amount of time it takes to transfer one byte from disk into main memory, given that the data is already directly under the head, even that time is about 4 times larger than the amount of time it takes to access a particular byte in main memory. The other thing to note about hardware here is that the transfer of data from disk happens in chunks called blocks. So we don't fetch just a few bytes from the disk, we actually fetch an entire block. And that's because, again, if you've done a course on operating systems, you probably know about locality of reference. So if you're accessing a particular byte at a particular location on the disk, it's very likely that you'll be interested in the bytes that immediately come after this on the same track. So it makes sense to just fetch an entire block from disk into main memory because under the assumption that you'll be requiring the other bytes in that block as well. And the block sizes typically vary from 8 kilobyte to about 256 kilobyte. And one other thing is the section of main memory into which this data from disk is transferred is called the memory buffer. So this is the portion of the memory into which the data from disk is being written, or it's the portion of the memory from which data is being written to the disk. Now, when we talk about IR systems, typically what happens is the machine that is actually running the IR system is going to have several gigabytes of main memory, maybe 3 or 4, maybe tens of gigabytes, but not much larger than that. And as I just mentioned, the amount of disk space that is available on the hard disk is going to be 2 to 3 orders of magnitude larger than the amount of main memory that the machine has. The other thing to note here is that for IR systems, it does not make sense to buy very expensive machines that are fault tolerant. In other words, to buy machines that will never fail. Because such machines are usually very, very expensive, and the approach that in fact, all search engines today take is to use an entire set of machines, thousands and thousands of machines, or sometimes millions of machines, that are each of which is just a regular commodity machine. okay, each of which is not very different from the PC that you have. But by forming this huge cluster of machines, such that individual machines in that cluster may fail, search engines are able to be more effective that way. I mean, there used to be a time about 10 to 15 years ago where people used to talk about supercomputers. So these were computers that were very resilient to fault tolerance. They were very fault tolerant, and they had several processors which could process a large amount of data. But today we've moved more towards distributed computing, where we have a large set of computers, and each computer in that set is just a regular machine. And we don't worry about fault tolerance, because if one of the machine fails, then we can just reassign the task that the machine was doing to some other machine. So this is just these are just some typical figures for the average seek time, which includes the rotational latency also. Uh, it's about a few milliseconds, 5 milliseconds. I mean, these are not exact figures. Just think about the range. I mean, even if it's 10 milliseconds or 15 milliseconds in some machines, it doesn't matter. But the order of magnitude of the seek time is around a few milliseconds. Whereas if you look at the amount of time it takes to transfer a byte from disk to main memory, that's about 2 into 10 to the power minus 8 seconds. So we're talking about fractions of microseconds here. And the amount of time it takes to uh, transfer a byte from main memory, or to access a byte from main memory, will be governed pretty much by the processor's clock rate. So it's going to be about 3 or 4 times smaller than even the transfer time from disk. And we just saw that we are going to assume that the size of main memory is a few gigabytes or tens of gigabytes, and the amount of disk space is going to be much more larger than this. So the other thing that we are going to assume in this chapter and also in the next chapter is that we are going to work with a larger corpus than Shakespeare's collected works. So the collection that we are going to work with is called the RCV1 collection. The RCV1 collection is a collection of news articles that were wired from Reuters, which is one of the news companies, to various newspapers from one month in some month in 1995 or 1996 to the same month next year. So it's about 1 year of news articles that were wired from Reuters to the newspapers. And the newspapers would obviously choose some of those articles and then publish them in the news. So this corpus is going to be larger than the corpus of Shakespeare, but it's not going to be too large. We're going to work with this because this corpus is publicly available and it's more plausible, it's more realistic than the small corpus that we are working with in chapter 1. And we are going to see how to build an index for corpora that are typically of this size, because it's going to turn out that it's not so easy to fit such collections into main memory. So here's a typical Reuters RCV1 document. Note that we are going to focus primarily on the text data in the document. We're not worried about images and videos and so on. So these are some statistics. Again, these are just some assumptions that we're going to make. We are going to assume that we have 800,000 documents, which is pretty large compared to just the 37 plays of Shakespeare that we are working with. We're going to assume that the average number of words in a document is about 200. We'll assume that we have about 400,000 terms, distinct terms, in this collection as a whole. So this is going to be the size of the dictionary, 400,000 terms. And the average number of bytes taken by a taken up per word or per token in the document is about 6, which includes spaces and punctuation marks. And if you delete, if you ignore spaces and punctuation marks, it comes to about 4.5 bytes per word on an average. But the average number of bytes per term is going to be about 7.5. Now, one of the questions that may come to your mind right now is, why is there this difference between the average number of bytes per token and the average number of bytes per term? Why is this larger than this figure? Anybody want to take a guess? Recall the distinction between tokens and terms that we discussed in chapter 2. Why the average number of bytes per term would be larger than the average number of bytes per token? Does
Uh,
anybody want to answer?
so yes, sir, like in stemming and lemmatization and all that, we were cutting down the word size by a lot usually. Like running was getting stored as run, and even for stemming, like it was getting the word size was getting cut down. Like operation was getting stored as operat. So I think it could be because of that. Like
But you would expect the opposite trend, right? In that case, you would expect the average number of bytes per term to be smaller than the average number of bytes per token, because tokens are what you have initially, and after that linguistic pre-processing, you get something called a term. So why is the average word size of a term, average length of a term, more than the average length of a token?
so because of the index construction, like the n-gram indexes and all that, that would take up space. And
Okay, well, this is more a question about the English language than about stemming lemmatization or the n-gram indices that we've been discussing. Just think about the common words in the English language. Are they short or are they long? I mean, think about stop words, for example. Stop words are usually very short words, right? So if the common words in the English language are short in length, then you would expect them to bias the average length of a token to a small value. But if every word in the dictionary is weighted the same, right? Because for calculating the average number of bytes per term, you need to give equal weight to every term. In that case, the rare words which are longer will have the same weight as the common words. And so the average length will be larger, right? Because short words are the common words in the English language. Okay, and which is why the average number of bytes per token, where if the word appears 100 times or 100 million times in the uh, well, here they can't appear 100 million times, but let's say they appear 500,000 times, uh, then they will be weighed 500,000 times in calculating this average, but they will be weighed only once when calculating this average. Is that clear?
so, could you please repeat it also? Please?
Sorry, I couldn't hear you properly.
So could you please repeat that once?
Yeah, so what I'm saying is, if you look at common words in the English language like and, the, in, on, and so on, these words appear a large number of times, right? So if you want to calculate the average number of bytes per token, note that the number of bytes per token is going to be proportional to the length of the word, right? So if the common words, if the words that are occurring, if the words that are predominant in the corpus are short words, then you can expect the average to be biased towards the short side. But when calculating the average number of bytes per term, you're not going
You're
to
not going to
you're not going to
you're not
count
going to count
a length of
a
one
length of
a
1
500,000 bytes.
500,000 bytes.
You're going to count
You're
it
going
this
to count it this month.
for the whole corpus. You're going to calculate. You're going to weigh this or this term a just once, right? So it's the average number of bytes per term is going to be the length of a plus the length of an plus so on. Basically, you'll add up the lengths of all the terms in the dictionary and then divide by the total number of terms in the dictionary. Whereas if you want to calculate the average number of bytes per token, then if A occurs 500,000 times in the corpus, then you will need to take 500,000 multiplied by the length of A plus 700,000 times the length of an, something like that. So these shorter words will be multiplied or will be counted hundreds of thousands of times when computing this average. Okay, so this is the total number of tokens. Recall that if when computing the number of tokens, you have to count every instance of the appearance of the word anywhere in the corpus separately. Whereas when looking at the number of terms, you just have to look at what terms appear in the dictionary, ignoring how frequently those terms appear in the corpus. So because shorter words tend to have higher frequencies, higher collection frequencies, this average is going to be smaller than this average. Is that clear now?
Yes, sir.
Okay. We are also going to work with non-positional postings in this chapter, which means we are not going to keep track of positions of terms within documents. And we're going to assume that the non-positional postings, not assume, but it turns out that the number of non-positional postings for this particular corpus turns out to be about 100 million. Okay, so this is basically the number of normalized tokens that are going to be indexed, right? Because each normalized token becomes an entry in your index. Well, actually, not normalized token because if you recall from chapter 1, we also removed duplicates, right? We also removed duplicates there. So the number of non-positional postings is simply the sum of the lengths of the postings list in the index, and that's about 100 million. And you can expect this number to be smaller than this multiplied with this, right? Because if there are 800,000 documents and on an average 200 tokens per document, then the total number of tokens in the whole corpus is 800,000 times 200, which is about 160 million, whereas this is about 100 million. And that's because duplicates are going to be collapsed when you're looking at non-positional postings. Right, so these are just some empirical values that we're going to work with. You don't have to remember these, obviously. This is just to show you what are the typical range of values that we are looking at here.